So let's take another look at parabolas. You thought you knew everything there was to know about parabolas, and that was until we came across this geometric definition of parabolas. So stay tuned. Okay, so this is Planet Numeracy. I'm Mark Nolde, your personal math coach. I've been teaching high school math for over 20 years, and that includes my 4 daughters. So if you've ever wanted to know more about the geometric definition of parabolas, stay tuned because I have it all lined up for you.
So originally we learned how to graph parabolas using this format. Right? We wrote it in general form, and then we rewrote it in vertex form or general form, and it gave us the vertex HK, and it would tell us if we stretched it or shrunk it vertically at all. We did not get into putting the B here, but this is how we were graphing the parabola. But there is another way to look at a parabola, and that is through its focus and directrix. So let's look at that. So our official definition for a parabola is the set of points that are equidistant from a specific point, the focus, F, and a specific line, the directrix, or y equals P. So let's look at another slide, and I'll show you what we mean here. So I'll do my best to graph this freehand. So what I'm drawing now here is the axis of symmetry. And a parabola has an axis of symmetry. So it comes kind of like this, and it's symmetric. That wasn't a very good parabola. Let me undo that. And it comes down like this. So this white line is my axis of symmetry, this white dashed line. So this is my parabola. So what are we talking about with this focus and this directrix? So a focus is a point, I'll do that in yellow, say right about here. Just doing this to show you what's what. That is called my focus. And we usually refer to that with capital letter F. And then we say it's equidistant from some line called the directrix. So I'm going to do this as best as I can freehand here. And this is called the directrix. So directrix is, oops, I spelled that wrong. It's got an X, directrix. So the distance from here to here is the same distance. And when it's on this line, we call that P. Other distances are also the same. So this distance from here to the parabola, and from the parabola straight down perpendicularly to the directrix, this is also the same distance. Or if I went out further and drew one and came down, this is congruent to this. And that is our official definition of the parabola in terms of its directrix and its focus. This point here has not changed. We still call this the vertex, and a lot of times we just use a capital V for the vertex. So we have our focus, our directrix, and our vertex. Bunch of fancy words there. So let's look at this in practice. So some textbooks will call this the geometric definition of a parabola, what we talked about back here, the geometric definition of a parabola. Now with that comes another geometric equation, and it comes in 2 flavors. The first flavor is this, x squared equals 4py. And that is the general form for an equation that is symmetric about the x, or symmetric about the y-axis. So it would look something like this. And it would have a focus up here. And we would say that's the focus 0p, because it goes up p units. And we would have a directrix down here. And the equation of that directrix would be y equals negative p, because this point here is 0, negative p. So that means, again, this distance is called p. So that's when we have one that's pointing up. If I had one pointing down, I could have that as well. But I would still use this equation here, but my p would have to be a little bit different to change this. So, but we do have this occasion here, where x squared equals 4 times py. And instead of pointing up, the parabola has the origin as its vertex. It's pointing down. And here's my focus F, and here is this dotted line, my directrix y equals p. Now this time it's p because this point is 0, negative p, and this point would be 0, positive p. But again, the thing to remember is this distance and this distance are the same. They're both the same distance, just called p. So let's look at a quick example. So let's consider this example. Simple example, y equals 1/2 x squared. We know this is a parabola from what we already know about graphing parabolas, but if we want to write it in a context where I can figure out what is the focus and what is its directrix, I want to write it in the form of x squared equals 4py. All right, now remember, p is the distance from the vertex to the focus. All right, so if I'm going to graph this, it's going to look like this. And say this is a 1 and that's a -1. I'm going to be looking at a focus somewhere in this neighborhood. I'll show you here just a second. First things first, let's take this, let's multiply both sides by 2. And that would give us the equation 2y equals, these twos cancel, so it's just x squared. So we think of it this way, x squared equals 2y. So now it's starting to look more like this over here. But 4p has got to be equal to 2, which tells me that p is 1/2, right? 2 divided by 4. So I can write this as x squared equals 4 times 1/2 times y. Now, why I want to write it this way is because then I can tell where the focus goes. So the focus goes 1/2 units above the vertex. So the vertex is right here, and 1 is right here. So at this point right here, 0, 1/2 is my focus, right? Put a capital F for that. And that means that because the distance from the focus to the vertex is equidistant from the vertex to the directrix, I can figure out that my directrix is this line right here, y equals -1/2, because the distance from, let me switch colors, from here to here, do it in green, is 1/2, and the distance from here to here is a green, which is also 1/2. So that is the benefit of writing it this way and of using this format in general, is that I can find my focus and my directrix pretty easily when it's in this context. But let's look at one that's a little bit more challenging. So this one looks a little bit different, not a lot different, but it has a coefficient of -2. So before I had 1/2, but this being negative tells me that I know this parabola is going to open downward. So one of the first things I will do is, just like before, I'm going to try to fit it into this form. X squared equals 4py, which means that 4p has got to be equal to -2. So p is going to be a -1/2. So very similar to the last example. So this is 4 times -1/2 times y. So again, this 4 times -1/2 is how we started with the -2. So what this tells me is my focus, let's switch colors here. So my focus is going to be underneath the parabola, say right here. And it's going to be 1/2 unit down. So if this was a -1 down here, let me make this a little bit longer. I can do that. And this would be 0 down 1/2, because that's where my focus occurs. The other thing I would have is a directrix a little bit above it. So this point here on the directrix would be 0 positive 1/2, and that would tell me that my directrix has the equation y equals 1/2. All right, the other flavor of these parabolas are the parabolas that have a horizontal axis. So I could have something like this, say. Now let me make that a different color. Let's go with red. Be Christmassy. Okay, now the definitions for the focus are still the same. So if this is a focus, this distance is still called P, except that this now becomes P, 0, because I'm not going up or down from this point. Let me make this look a little bit more like a P. And I still have the directrix down here, and this distance is still P. All right, so if that distance is P, that makes this vertical line be x equals negative P. So they just come in this other variety. And where we had x squared equals 4px, I have y squared equals, or we had x squared equals 4py, sorry. Going back here, we had x squared equals 4py. Now we're looking at y squared equals 4px. So we still are going to have the same things at play here. So we might end up seeing one that looks like this, say. Suppose I have, looking for an example here, suppose I have a parabola, 6x, let me go to a new page. We have 6x plus y squared equals 0. So when I look at this and I see I have a y squared, not an x squared, I know this is going to be a sideways opening parabola, one way or the other. But I'm going to write it in this form. I'm going to write it in the form y squared equals 4px. So that ends up being y squared equals negative 6x. So that means negative 6 is equal to 4p. Or that p equals negative 3/2. So that tells me that when I look at a graph of this, let me make a quick graph here. My focus is going to be, from the origin, is going to be 1.5 units. And this time, because of this negative sign, I'm opening up this way. I'm opening up to the left because of the negative. So I have a focus right here. So if I call this F my focus, it's going to be at negative 3/2 because I went 3/2 to the left, right? To the left, correct? And that would make my y coordinate be 0. Now the other thing we have is going an equal distance. This is my distance P, which is 3/2. If I go, draw through here. If I draw through here, so I'm also 3/2 distance here. This point is positive 3/2, 0. But more importantly, I have a directrix that is x equals 3/2 because it's a vertical line. So because it's a vertical line, it's x equals. There's no y because it's not crossing the y-axis at all. It's only crossing the x-axis. All right, so that kind of talks about two of the different flavors there. Let me give you one more thing to think about. All right, so here's one more thing. This is kind of interesting. So here's a parabola, right? It is centered down. It's symmetric about the y-axis. And I have penciled in here my focus and then, of course, the directrix. So this distance is P that I'm pointing at, and this distance is P. Here's another interesting thing. I'm going to draw red. If I draw at a right angle, right, to my y-axis, this distance ends up being 2P. And same as here. This distance would be 2P. It's got to be at a right angle. And this total distance from here to here has kind of an interesting name. But from this endpoint to this endpoint, use my pointer, from this endpoint to this endpoint, this is called our latus, L-A-T-U-S, rectum. And that's why I said this is kind of a funny name. But this distance from here to here is called the latus rectum. Let me make that look more like lattice, L-A-T-U-S. Gotta erase a little bit right there. So latus rectum. It's got to be Latin for something. What, I do not know. So anyway, it's also called the focal diameter. So this is the focal diameter. So from here to here, from here to here. Focal diameter. Now another interesting thing is that if I draw a perpendicular from here to here, that also has the distance of P. Naturally, because this is P. And it's also P down to the directrix. So kind of an interesting thing that this is 2P and this is P. So a couple of new pieces of terminology. The latus rectum, which is this. I keep drawing on it, but from here to here. Also known as the focal diameter. So the focal diameter. And that comes to play with applications of a parabola. So what is a parabola good for? Let's do one more slide just to explain that. So have you ever driven in a car? If you have, then you know cars have headlights. So this is a parabolic mirror on the inside of a headlight. So I'll point at it from here to here. And this is the light source, which points back towards the mirror. And everywhere it points, the mirror reflects. And guess what? The mirror, wherever the light is shined, ends up shining outward. Whoops, light doesn't go crooked like that. Shines outward like this. And this is, mathematically, this is a parabolic mirror. It's shaped like a parabola. And this would be the focus. And if the focus is in the right place, the light source, then all of the beams of light shine directly forward. And that is one application, simple application of a parabola. Kind of corny, but hopefully you liked it.
Okay, so that wasn't too bad. So question of the day, always remember that there's no such thing as a dumb question. It's dumb not to ask. So whenever you're in your classes, ask a question, and if you have a good teacher, they're not going to make you feel stupid for asking it. Having said that, don't forget that math is not a spectator sport. If you want to learn math, you have to do math. Remember to embrace the opportunities to learn from those tough problems on your assignments. So go ahead, like, subscribe, share, comment down below. Be sure to share this with somebody who you think might benefit from it. And until next time, this is Mark Nolde signing out.